All right, welcome back to Unit 3, Work, Energy, and Power here in Physics C. So now we're going to start talking our conversation away from the works part of it. Now we're going to keep talking about kinetic energy, but also bring in this potential energy. So this is going to be a lot different than what you saw last year in Physics 1, if you took Physics 1, or if you've taken any other non-calculus-based physics, because now we're going to hit calculus pretty hard, right, moving forward with potential energy. Okay, so potential energy is energy associated forces that depend on position and configuration of an object relative to its surroundings. And two of the big conservation or potential energies that you're going to see are going to be those involved with gravitational potential energy, which is what the roller coaster is, and also spring potential energies. Okay, so potential energy is defined only for conservative forces, so forces that are going to conserve energy. And so to find to find potential energy, it's going to be the negative integral of f dx, okay, where this f is a conservative force. Springs, gravity, or the force done by gravity, or weight. I can show you the derivation of those equations, but we don't have to go through all that, okay? So the first common example of potential energy is what we call gravitational potential energy, or U sub G. And so the conservative force that is acting on the object in this case is going to be the force of gravity, which, remember, we call the force of gravity, it's an object's weight. And we can simply calculate that by doing U sub G equals mgh. So mass times gravity, or acceleration due to gravity, times the height, okay? And then the second one will be the spring force, right? The one that we talked about when we talked about the work energy principle. And so it looks very similar to the work done. In fact, when we get down to the end, yes, potential energy is the work, essentially the work done by the conservative force. In a way. So UG, right, gravitational potential energy, is the work done against the force of gravity. USP, or US, right, is the work done against the spring, okay? And so sometimes, though, you do have to talk about, any potential energy, right? So the potential of any conservative force, actually, so this should say the potential energy of any conservative force can be determined by finding a derivative. And you kind of see that here. So these two kind of equations go together, right? Potential energy is the negative integral of f dx, where force is the negative derivative of potential energy. So when you do these, the first thing you do is to establish a reference point. Okay, and simply enough, that is when x equals 0 meters, right? So like for a roller coaster, it's going to be way down here at the bottom. For a spring, right, it's going to be when it's relaxed or in its natural equilibrium state. Okay, so let's look at how this works, right? So if I want to find the force associated with this function, so suppose that u of x is equal to negative ax plus divided by b squared plus x squared, where a and b are constants, so we don't have to worry about what they are. Okay, what is the force associated with this function? So we know that f is negative du dx. So we're going to take the derivative of this. Now, so because what you see here, this is going to be the quotient rule. So you should have learned about this in your calculus class. And the way I like to talk about it is low d high minus high d low over low squared. Okay, so when we say d high and d low, we're talking about the derivatives. So we're going to take the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Okay, so I'm going to say negative d dx of this function, so negative ax over b squared plus x squared. Okay, but because negative, I can pull negative a out in front, and so that makes it a positive. So I'm going to find d dx of x over b squared plus x squared. So my low is b squared plus x squared. My high is x. So my d low will be 2x, and my d high will be 1. And now I'm just going to fit it into my little low d high minus high d low over low squared. It's going to be a times, so I go low d high. So b squared plus x squared times 1 minus high d low, so x times 2x divided by b squared plus x squared. And now I just simplify. So I'm going to have a, and so this is going to be b squared plus x squared minus 2x squared over b squared plus x squared squared. I forgot the squared over there. So I got x squared minus 2x squared. That's negative x squared. I'm going to bring that. So I'm going to have a times b squared minus x squared over b squared plus x squared squared. So that would be the force that is associated with that potential energy function. Okay, so again, this is a little calculus. You can be given the opposite as well, right? And asked to find what is the potential energy with this force. Okay, and then you could go the opposite way. Okay, this right here and the integral piece are going to be very important for the last video when we talk about potential energy diagrams. Okay, but before we do that, we're going to talk about conservation energy and power.